Welcome back. Good morning to those of you on US time. Good afternoon and evening to those of you on other times. Thanks so much for joining us for the last day of PyaR. Today, we're going to leap right into where we left off because we want to be able to cover all the notebooks, all the important Python resources in them. Today, we're going to pick up where we left off at Notebook 4. Before we do that, I'm going to give us a brief recap of Doppler shift. And Doppler shift is that phenomenon that we saw. All right, I want to not share that screen. I want to share Google Chrome. All right, there we are. All right, Doppler shift is that phenomenon we get when an ambulance drives towards us, and as it approaches us, the waves of sound emitting from it compress and become higher frequency or shorter wavelength. Same thing happens with light. When something moves towards us, you get that compression, shorter wavelengths, moves further away from us, those wavelengths elongate and stretch. We call this redshift. And the way that applies to astronomy is we can use that shift in, for example, a spectrum. We know what a spectrum of light coming from an object should look like. We know where this absorption line should be if we were standing right up next to the object. We call it the rest wavelength. But by the time it reaches us, it is either red shifted, stretched, or blue shifted, squished up, which allows us to do things like extrapolate how fast it is moving away or towards us. The way that we relate those two quantities is by this Doppler shift formula here. And the quantities we see herein are that rest wavelength, imagining we're standing right next to the object, and the wavelength that actually reaches us. We're going to call that wavelength nu. Now, I understand I have some construction going on outside my window. Can everyone still hear me? Okay. All right. There is this formula that we're going to be using when we put in our equations. So to go over the quantities, the velocity, if v is less than 0, the star is moving away from us. If v is greater than 0, the star is moving towards us.
Other
And
way around,
velocity,
Maddie. Maddie, other way around. Positive velocity is away.
no, Raj, this is updated to be what it is in the notebook.
Right,
Based
right.
on
What you've written is correct. What you said was the opposite. Sorry.
okay.
Sorry to interrupt.
No worries. Better to say it out loud correctly. And then c is our speed of light, which we're using in kilometers per second in our notebooks. All right, so we're going to remember this equation as we go over to our notebook. Opening up notebook 4, we see this is an activity in radial velocity. We're going to go through our classic steps. We're going to import NumPy and matplotlib. And to remind everyone what this little percentage sign with this command matplotlib inline does, it's not really relevant in most modern Jupyter notebooks. They actually do this themselves, but if you're using an older version of Jupyter for some reason, you always want to do this. So it's going to create your plot right there in line with all your other cells. All right, so we can read here that our folder has spectra of 3 stars. Or sorry, 3 stars, and these have different names. We're going to use these names. We're going to measure the radial velocity of these stars. So we're defining a function here, and what this function does is it allows us to shift from whatever that rest wavelength was. Lambda is that symbol you saw here, this lambda, to a new lambda, given whatever velocity we're going to input as an argument into this function. Remember, these things in the parentheses of a function, those are your arguments, those are your inputs. All right, so this obviously isn't correct. We know that redshifting is going to happen, so we need to relate our new lambda to our rest lambda. And hopefully by now you connected that we're going to be using this equation here. So we know that we want to get the new lambda, so we know that rest lambda is 1 plus v over c. So rest lambda times, and it's very important that I put those parentheses, otherwise it won't do order operations, just like it wouldn't on your calculator. 1 plus v divided by c. What would happen if I ran this as it is now? Let's try it actually. All right, shift to moving. I use the tab to auto-complete that. Rest lambda, let's say, I don't know, 1,000. And let's say a v of 100 kilometers per second. Make a prediction now what's going to happen. All right, let's execute it. Oh no, we got an error. And why is that? We didn't define our C. So C is a constant in here, so we do have to define it. So C equals, and then I mentioned this is going to be in kilometers per second. So we're going to do 3 times 10 to the 5. And since I like to use scientific notation instead of writing out 5 zeros, I'm going to write it as 3e5. And that e is not like e you might have seen in math before, where it's e to some power. E is not 2.818. E is a way of writing 3 times 10 to the 5. I could also write this as 3 times 10 raised to the 5th. And I, of course, could also write this 1, 2, 3, 4, 5. I don't write 3e5 because it's easier. Sorry, quick reminder, what I did there was incorrect. 3 times 10, and the way we write raised in Python is 2 little stars to the 5th. We don't use that caret symbol. That's what we'll use in other codes. All right, so now we've defined our function correctly. Deleted that cell. All right, so if we want to follow this prompt here, we're going to test what happens when we shift to moving with these 2 velocities here, 20 kilometers, 200 kilometers per second, and negative 200 kilometers per second. And to recall, negative velocity is going to be moving towards us, positive moving away from us. All right, shift to moving. I tab to autocomplete. I'm going to put in the variable name to avoid having to retype 6563 over and over again. Rest, and then I tab to autocomplete there. And then I need to have put our other argument in there, which is v. If I tried to run it without putting that argument in there, it would give an error about me not having put that v value in. So our first one we were supposed to put in was 200. And I'm gonna get fancy here. I want to print these both out at the same time. So the easiest way to do that would be simply to put a print statement around this. This will print out whatever is in here. And then I can do the same thing with negative 200. And we see our values here. But sometimes that's not super informative. Sometimes we want to get a little bit fancier. So another way we can do this is we can make a statement. And there's a couple ways to format this. Yesterday we saw formatting strings using the dot format. Today I'll show you another way, which is to use this percent symbol and then put the same percent symbol in front of our output here. And I'm gonna say percent, and however I want to format this. Let's say I want one significant figure after the decimal point, maybe 2 significant figures. And then I want this to be in the format of a float instead of like scientific notation or anything else. All right, so that'll give me a float, and then I put kilometers per second. So what happens if we print this out now? It gives us a value in kilometers per second. And I can even make it more informative, like the rest. Sorry, new wavelength is, I'm sorry. Oh, anyone catch what I did? Units are incredibly important. It's early here in the morning in California, and look what I did. I forgot that the output is not, in fact, a velocity. This is a wavelength. We're shifting to a new wavelength. That's, in fact, why it was helpful to write out that whole sentence about what our output actually is. So new wavelength is, and we did this all in units of kilometers. We actually
I think it's angstroms.
angstroms. Okay.
6563 should be the H alpha in angstrom. Yeah.
So yeah, to have that many numbers is probably angstroms, and angstroms are 10 to the negative 10 meters. All right, new wavelength is that many angstroms. Okay. So in fact, it was not just a silly example of how to format a string, there's actually a really helpful way of interpreting your data can be really helpful. So you can do a sanity check. You can say, wait a minute, does that result make sense? Or, oh, I actually put the wrong units on that result or misinterpreted what it was. Okay, so now on to our 3 stars. So we're going to pick one of these stars, and these are their names, these long strings of numbers. And we're going to pick a template name. Remember that we have created these in other activities. So let's pick a random star name. I'm going to pick the first one because it's just right there. So I'm going to copy it into here where it says star name goes here. And this is a string. So that string is going to go into here. And when we put the plus signs between two strings, it concatenates them. And concatenates means it sticks them end to end. And it's going to be one continuous string. And template name here. Let's do RGBs. We looked at RGBs yesterday. Okay. Then what these following lines are doing, just like yesterday, this load text is going to load up this file that's given here at this location. Remember that these dot dots say go up one folder and then back down into another folder called data. And then we're going to unpack it. So we're going to make each of those columns. The first column will go to psi lambda, and the second column will go to psi flux. So let's execute it and see if we've been successful. All right. No errors have come up. Let's move on, assuming this has worked correctly. So what are we doing next? So we're going to try to guess at our velocities here. So I want each of you, I'm going to choose a guess and we can look at my screen and guess. I'd like each of you to follow along and make your own guess. We were given the number 200 before. So let's guess 200 again. What we're doing here is this new temporary lambda. This is just saying we're not going to keep this variable forever. You can name a variable whatever the heck you want, but it's nice to say temporary if you're not going to keep that value forever. We're shifting to, we need to define, template, not temporary, template. Template lambda here, we loaded in from this template file for what a default RGB star was. We're going to shift to the moving to our bguess. And then we're going to plot it. So we're going to plot the spectrum that's here in this file. Lambda and flux allow us to plot a spectrum, just like here in our example spectrum here. Flux will go on the y-axis and wavelength will go on the x-axis, and that tells us how much flux is at each wavelength. And that gives us the information we need to see if our guess is good for how much the regular RGB star and this actual star have been shifted over, how fast they're moving relative to us on Earth. Okay, we're going to execute it. Actually, before we execute it, let's make some predictions. We see this is going to plot lambda on the x-axis, flux on the y-axis. We can tell that we're going to be plotting one in black and one in red. Nicely, we've labeled these to include the template and helpfully the template name and the star name. And whenever we use label, if we want it to show up on our plot in a legend that tells us what line is what color, we need to call this plt.legend. And then we're setting our X and Y labels, as always, just very important. So we have a prediction of what it's going to look like. What does it actually look like? Just going to take a second to load. Must be a lot of data. Okay. So, does this template look like it's a good match for the star? We know that they're supposed to be shifted relative to one another. But do these even look like the same star? Do you even have the same shape? I would hazard a guess and say no. I think these two don't look very much like one another. So let's go back up here. And instead of an RGB star, let's try a main sequence star. We're going to load that up. Now this template lambda and template flux are that of a main sequence star and not an RGB star. Our science and the science flux should be the same. And we're going to load it up. So while the print goes on a lot of data. Okay, look a little bit closer. I'm still not really seeing the same shape here in the red in the science as I am in the template. Let's try one more time. Maybe that's our best fit, but maybe it's actually an AGB star. So we're going to plot the AGB. Go back to here. Remember, of course, we still have to shift it. 200 is kilometers per second. It's just a guess. Oh, okay, yeah. I feel pretty darn good about that being the same type of star. It's okay that they're not exactly the same features here. There's probably something in the atmosphere of this star or between us and that star, like gas in the way, that is causing this feature here in the black line that's not in the red line. Or something that's emitting more flux in this section in our actual star than in the template star. We can see that the main features here are the same. This line looks approximately the same. And as it turns out, our guess of 200 wasn't actually that bad.
Maddie, if I can chime in for a second, if you
Mhm.
zoom into the region around 8500, so if you go 8450 to 8700, you'll
Okay.
see the calcium triplet in detail, and then you'll be able to set a finer velocity. So if you go, yeah, I think 8400 to 8700 is good.
So what I'm doing here, you all want to support me, please, in parentheses, is I'm defining a new X range on our plot. Give it a second. Okay.
And you see those two dips, those prominent dips, one at 8550 and one at 8650. You can see that the science star is offset to the left relative to the template. So the template needs a more negative velocity to match.
Okay. So let's make another guess. Let's make sure that's what our prompt wants us to do. Play with EV guess until they're lined up. Well, it's a good insight Raja had because it looked to the naked eye like they were pretty closely aligned. But then once we zoom in and we see those individual features, then really, really closely line these up. Just make
And,
them more negative. Let's
and
try.
those, there are actually three dips there. The third one is very faint, but the third one is sort of buried in the noise. But once you shift it, you'll see it. And this is produced by calcium ions in the atmosphere of the star, singly ionized calcium. Ah.
So 100's not going to do it. All right, let's keep track of it. Our black line is to the right now. We want our black line to shift to the left.
Yeah.
Okay, let's try negative 100. Getting closer. Okay, and our black line on top of our red line. Let's try negative 200. Ooh, okay. Maybe a
Use,
little less than negative 200. Raja, what's your professional
yeah,
assessment?
a little bit more negative even. You can see the
Okay.
dips don't quite line up, right? So yeah, see that's doing better.
And negative
And that may be a little
200.
bit too much, but so
Yeah.
minus maybe minus 230 or something like that. Yeah.
Let's try 230. Yeah, because then the other features we can see do start to line up.
Yeah, you see those fainter features weren't visible before. But once you do this, you start to see it. You see that step at 8600, everything starts to line up once you get the right I mean, there's noise also, so not everything will line up, but you can start to see that there are real features that are otherwise buried in the noise.
Mm-hmm. And this is, in fact, how we really do this. This is how we tell how fast things are moving, how far away they are, because remember we made that connection between how redshifted a spectrum is and how far away it is if it's far enough away.
And
All
Maddie, I
right.
wrote up, sorry to interrupt again. I wrote up a one pager on cross correlation at some point. So if people are interested, I can send that around. And this is actually a very powerful, I mean, so we don't do this by eye in reality for thousands of stars. A computer does this, but it's a very powerful technique called cross correlation that is actually used for page ranking and how a lot of Google works when you search. You're actually
Yeah.
looking for a pattern match.
Cross correlation is really fun, you all. What it is we just take this black spectrum and we slide it from side to side. We say, is that a good match? 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 Is this a good match? Is that a good match? Is that a good match? And it ranks how good of a match it is, and then chooses sort of the best one. Literally just slide side to side like that. It's really fun. Okay,
Yeah,
so we have a good guess of what our velocity is. Does Raj want to make a comment on this one more time before we move on?
I think it's good to move on. This is good. Thank you. Thank you. Thank you.
All right. So on your own, I want you all to play with that VA guess value, try it out for each of these three stars, and fill this out. Decide which star it actually is, and then what velocity it is. And remember, it's really nice to experiment by putting some extreme large values just to see what direction does it move it in to go this way? What direction does it move it in to go this way? All right, radial velocity maps. This is what I alluded to us doing yesterday when I said we have to think about the fact that we returned to that paper, we'd see that we took a picture of the southern half of Andromeda. And Andromeda is a almost side-ish on spiral galaxies, a little bit like this angle. And so all the stars on one side, because these spiral galaxies rotate, just like our orbit, stars orbit around the center, and rotates just like our Milky Way. Then all the stars on one side should probably be moving in about the same direction. So let's see if that's the case. All right, so we're going to read in another file. This is that same data we used yesterday when we were plotting our color magnitude diagram, the Hubble Space Telescope data about stars, and from Keck as well, which is a ground-based telescope. I'm inferring this from the name. All right. So to break down finally what these actually are, RA and DEC are units of coordinates that are on the night sky. And these are angular coordinates, which means that because the sky is a sphere around us, as we move from, say, point A to point B, it's actually subtending an angle. Our sky is not flat, so we can't go, this is, a finite distance. That's not as helpful as it is to say, oh, it's actually this angle away. But xi, which is this xi, xi, and eta are just different units of doing it no longer in degrees, like this, that angle that RA and DEC describe, but actually just giving it like a sort of a finite distance from here to here. And so xi and eta are like our x and y coordinates on the sky. And we're turning that into the units of kiloparsecs that we heard about from Peter yesterday. And it's just, we just trust that this factor is how we're going to convert that given the distance these stars are. All right, so we can predict what this plot is going to do here. We know that we're going to have xi on the x-axis and eta on the y-axis. So these are sort of our x and y coordinates again on the sky. We're setting our limits here. And what they're doing here when they call this aspect equal, it's actually pretty important in what we're doing. Because both of these, xi and eta, coordinates are in units of kiloparsecs, we don't for some reason want 1 kiloparsec on the x-axis to be this long and 1 kiloparsec on the y-axis to be this long. That wouldn't give us a realistic representation of what it would look like on the sky. We want each kiloparsec to be equal on each axis. So that's why we use the aspect equal, aspect ratio, kind of like on your TV or computer. I want it to be equal. All right. So the reason that ACE is labeled CC here is because we want to put it into this color bar command. What the color bar allows us to do is we can plot all these scatter plots using specific colors. And those colors are going to correspond to the velocity. Remember, C stands for color. We're plotting our eta and xi and eta, so x and y coordinates. We're giving each star a color, and that color corresponds to its velocity. It's saying choose one based on this. And then, well, we could guess that probably, like bluer means slower and yellower means faster. But we don't actually know until we put a color bar. And a color bar is going to tell us this shade of yellow means this speed, this shade of blue means this speed. All right, and what we're setting here with Vmin and Vmax is a lower limit on that color bar and an upper limit on that color bar. So we're saying, don't try to give me a color of negative 1,000 kilometers per second, because I know I don't have a negative 1,000 kilometers per second star in there. And if you give that really, really big range, then you're going to lose information about the actual range of stars. It'll be hard to tell a negative 700 from a negative 800 star if your range is too big. And the CMAP Vidrius That's how I knew it was going to be yellow and blue. Vidrius is a yellow color, blue color bar. So what do we get? We indeed get a yellow and blue map of our stars. And see here that 100 is in yellow. So now we see these bright yellow points. We know that these stars are moving positive 100 kilometers per second. And that our darkest blue stars are moving negative 700 kilometers per second. Now remember, negative in this case is moving towards us. So already with our eyes, we can see that this bottom edge is moving towards us faster than this top edge is. So that's, I mean, we can see that with our eyes. Let's use a different color scheme to make our story, our science story, a little clearer. So let's sort of choose a more intuitive color map for red and blue. We're going to plot the exact same thing here, but we're going to change our color bar. So we're to choose our color bars, we're going to go to matplotlib. You can tell how often I look this up. We don't want list of names colors. We want matplotlib color maps. So I'm going to look at these color maps. So color maps may sound silly, and just like an artistic choice, they are incredibly important too for depicting your science. Human eyes are really good at picking out color differences in a way we aren't about other things. And so we can really tell new trends, new data information from choosing good colors. And in fact, back in the day, when they were plotting the cosmic microwave background, they were plotting up that residual energy that's in every direction, deep in the past of our universe, and they were mapping it, and they thought they had a pretty good idea what it looked like. But they turned out they were using a color bar or a color map that was not perceptually uniform. So what happened was they were actually erasing information about the bumps and wiggles of the cosmic microwave background because they had chosen a bad color bar and a bad color map. So it actually is really important because our human eyes are really good at picking out color differences to choose a good color map. Now, for our purposes, we don't super care that these are ultra precise. I would say let's use one that has a red on a blue on it because we want to make it clear that we're red shifting and blue shifting. So I'm gonna scroll through so until I find, I think it's called red blue. Yeah, red blue. Let's choose RDBU is what I'm going to use. Or seismic. Actually, I like seismic. Seismic. All right. Does this look like what we want it to do? Remember, red shift is when something's moving away from us, and blue shift is when something's moving towards us. Indeed,
Let's
these are
see some answers in the chat. We're not getting too many chats today.
okay. I can't see the chat here, so
Yes. Let's see some guesses. Is this correct? Do you think this is correct based on the velocity bar and what you learned about blue shift and red shift?
does anyone see a problem here?
If somebody says no,
Okay, what
Amy
if
has said no.
I think Amy's on the right track. Color shift left, blue on top. Well, let's take a look at this. What is it happening at negative 100? It's also red. We want 0 to be blue. Or sorry, 0 to be that white in the center. So I'm gonna do something. There are more
So Maddie,
nuances.
this is actually very good because um, the color bar as it stands, you'll see that if you go to 0, 0 on the map, where there's no data actually,
0.
but you can guess that that's a color somewhere between blue and red. And that's being mapped to minus 300, which is the speed at which Andromeda is moving towards us. It's like a frisbee. Someone throws a frisbee. The frisbee is both spinning and it's moving towards us. The speed towards us is 300. And the red side, the spin is is away from us. So it's countering the motion of the frisbee towards us. So it's less negative. It's even positive in certain parts, right? It goes to some black colors or 0.
That's really interesting that that actually is a code for the relative velocity. But what we're going to do just to depict this so that our eyes can easily pick out the differences, we're going to do what I said is not a good idea, just as a cheat. There are more nuanced ways to do this, but we're going to make our upper and lower limits even so that it'll hit white when it's at 0 kilometers per second. We're going to lose maybe a little bit of information that our eyes can pick out. But now we see, oh,
Yeah, and you've got this. You've got 0 in the upper part. This is exactly where the speed of rotation and the translation are canceling each other, and that's the upper part of the galaxy. The top part of the galaxy is sort of whitish. And you'll see a little patch of white at the bottom. That's a companion galaxy to Andromeda that's not moving with its disk. There's a little
where is
patch
that, Raja?
right at 0, -6. Yeah, 0x and -6 and y. That's M32. That's a companion galaxy.
Oh, this here.
No, not the overall patch, but the white at the center of that dark blue. The dark blue is the disk.
Oh, interesting. Okay, cool. All right, so what is this telling us? Telling us overall that our arm is blue shifted. Now, if I'm remembering correctly and inferring from this plot, I would say the center of the galaxy, which is not moving as fast relative to us, is up here, and then the arm of the galaxy, which is moving very quickly towards us, is down here. Is that correct, Raja? Raja, you're muted.
The center of the galaxy is at sort of 0, 0, where it's so crowded that we don't have, so 0, 0 and x and y. And there it's so crowded that we don't have any, we can't make any direct measurements like this, because these are resolved stars. And so the center of the galaxy is too crowded for us. But you can see that the lower part is more blue shifted. That part is rotating towards us. And the upper part is effectively redshift and blue shift have canceled. Translation and rotation have canceled in the upper part.
So what's happening here, and he says translation is Andromeda moving, the entire galaxy moving, and then the rotation of the galaxy and this upper part essentially cancel each other out. So we are seeing the whole galaxy in this
Right,
case.
yeah.
Okay, so we see that we're mostly blue shifted and mostly everything's moving towards us. We can make an inference about what the average velocity is from these colors. You can put the color map back to whatever you want in order to make that inference. You may even look at this one. Looks like kind of greenish on average. Maybe it's like around, I don't know, 300-ish for the average. And so using these different color schemes, we can not only get information about how fast everything is moving in each location in the galaxy, we can also sort of do that by eye averaging to get information about the bulk velocity of the stars in the galaxy, or the systemic average velocity of Andromeda relative to us. All right, we're moving on from there. I think we pick up next with, is it who's our next mentor?
Let me check the agenda.
I think Hero might be doing something next, right? I can't remember. Hero,
Yes.
is that your next? Okay.
Yes, right before we move on to notebooks 5, right?
5 and 6,
We're
5
gonna
and
have a little
6.
bit of context on the on galaxy mergers.
Wonderful job, you all. I know it's a last day of some long days. Thank you for sticking with us. You can always revisit these notebooks if you filled them out. There are resources with filled notebooks and all of the slides that we've used in our presentation, and these recordings will be available. So revisit them when you're feeling jazzed and energized to do so. Thank you all for participating.
All right, I'm starting to share my screen. Let me know when it's visible. Remember that I have some lag issues sometimes, so I turned off my camera just to make it easier. In a second, it will be ready.
In the meantime, let me just say thank you, Maddie. That was terrific. Really good. And Notebook 5 will reinforce this because it's a model of a rotating galaxy, so you'll see all that in detail. And we can see your screen great, Hero.
Perfect. Okay. Give me a second till it's completely ready here on my side.
I recognize those slides, Hero.
Definitely. As I said yesterday to Madeline, we're standing on shoulders of giants. Okay, so let's start talking a little bit about galaxies and galaxy mergers. Now that we had some also idea of some measurements that have been done using this amazing tool, which is the Hubble Space Telescope, one of the most incredible devices that humanity has in order to explore the universe. We have been talking a bit about Andromeda Galaxy, but we can also start by introducing our own galaxy a little bit. Some of you might have heard that we are hosted by a beautiful solar system, but that solar system is also hosted by a huge, huge collection of stars, dust, gas, many things that conglomerate into a single thing that we call our home galaxy, the Milky Way. And here, let's see, I'm going to try to run this video. This is the view of a night sky. Hold on, let me see if this is properly showing. Okay, I think it's lagging a little bit. I will restart it, no problem. So here we have the view, like a time-lapse view of a night sky, following a little bit the movement or the apparent movement that the disk of our Milky Way has through the night. So if you go out and you have a very clean, like very clear sky in a very dark spot, which are sadly each day harder to come by, you will probably see this very incredible view. It's actually amazing. I hope most of you have had the chance or can have the chance at some point to see the disk of our galaxy with the naked eye, which is a very nice experience. It's very beautiful. And this has been for centuries, millennia even, topic of discussion for humans that stop and try to have a peek of the night sky. You know, there is this huge spot, or this huge like band that covers the sky between the stars that for many cultures has meant many things, and it's been actually pretty confusing. There is like this funny anecdote. I don't know if the people that live in the US are more familiar with it, but I've heard that somewhere in the end of the 20th century, there was like a blackout in Los Angeles at some point, and it got so dark that people in the city, many people were able to see for the first time the disk of the Milky Way with their own eyes, and they freaked out. They thought that something really bad was happening in the sky that had something to do with the blackout, and there were many calls to the emergency line because of this rare sight of something that is covering the whole sky, and it turned out to be the Milky Way. And just that many people are very detached with this view nowadays. So let's move to the next slide, where let's shift our sight a little bit. We know that this movement is apparent. This is not the true movement. It's not like this whole cloud is moving around us. This is not a cloud like our clouds that we see in our atmosphere. It's not an atmospheric phenomenon. This is actually something outside of our Earth, and even outside of our own solar system, that is there persistently, that has been seen for millennia, as I mentioned earlier. So we have this view that is very trippy, I want to say. It's like something that we're not used to doing, and it's like, okay, let's focus on how our Earth is the one that is moving, and then we see how the disk persists and it's actually there, and it's our planet and our solar system that is moving inside of it. So that is a very interesting way of seeing the movement of the night sky and trying to focus and follow the Milky Way. So that is a very interesting view. So yeah, so this is our galactic host. This is the Milky Way, beautiful galaxy. This is an artist's impression. There is no way that we can go this far out of our own perspective that we have orbiting the sun. that we can take this snapshot. We cannot go out of our own galaxy and take this picture, because this is a picture that is imagined, taken from even millions of light years away. So it is a view that we will not have, because just the sheer distance is so immense. But this is thanks to a lot of research and mapping that we have done, following the dynamics, the kinematics also of the stars and the gas and the dust and all the structures, smaller like parcels of material that compose this huge structure that is our galaxy. We can follow and measure, for example, with what Madeline was showing us. We can have very good measurements of the stars and the parcels of material in our own galaxy that allow us to construct maps like this that tells us, okay, this is the structure of the place you're living in. It's crazy and it's very fun, because it's like if you were locked inside of a room in your house, for example, and you had never seen your house before. It's like just doing something from your room that allows you to infer the shape of the rest of the house without looking at it. So it is very crazy sometimes that we have to devise different methods that indirectly can allow us to construct these kinds of images. And it is a very interesting site. And you might wonder, okay, so in this map, where are we? And this, not to scale, very important, this is the location of the solar system. So our sun is right here with the Earth, and is going around the center of the galaxy on an orbit that goes on for millions of years. It takes around 200 million years for the sun to go around once around the center of the galaxy. We should not make the very usual like mistake or misconception that there is something like a singular thing that is very heavy that makes the sun go around. There is actually a supermassive black hole in the center of the galaxy, but this is not what drives the movement of the sun around the center of the galaxy. It's the sheer mass of hundreds of thousands, even millions sometimes, of stars. It depends on the galaxy, that are coexisting in this huge system. Their collective mass and the mass of the gas that composes the galaxy is the thing that gravitationally rules this environment. So this movement of the sun and the other stars around the center of the galaxy is driven by the mass of the whole system. This is a very important thing to think about. Many people say that, okay,
Heroes,
oh yeah,
sorry to interrupt you.
no problem.
Is there a way you can move your zoom bar to the
Sure.
bottom or somewhere?
It doesn't block the titles.
Yeah, I think it's covering the title. Yeah, thank
Now
you.
it's better?
It's covering a different part of the screen, but I think people got the whole thing. It should be fine.
Okay,
It
thanks.
should come through in the
Perfect. Thanks for
recording.
pointing it out. No problem. Okay, so yeah, just this is, as I mentioned, the artist impression. And yeah, let's move on. So as I mentioned, there is a supermassive black hole in the center of our Milky Way. This has been proven very interestingly by studying the movement. It's always that when you want to understand the shape and the evolution that galaxies are having, you try to track the velocity of the individual stars that you can observe. So as we were doing with the notebook before, we have measurements of the radial velocity of stars in other galaxies, but also in our galaxy, that allow us to understand how things are happening and how things evolve with time. And in this case, yeah, it has allowed us to understand the shape of our galaxy, but also what's happening in the very center of our galaxy, where it is very dense and very hot. So, okay, let's continue. And we are currently standing at around 25,000 light years away from the center of the galaxy. You remember that yesterday, if you were in yesterday's session, we mentioned how we in astronomy don't use too much light years, like for data analysis. We tend to use more parsecs. So if you were to convert, you can try this exercise. If you were to convert this 25,000 light years of the sun's galactocentric distance, so this is the distance to the center of the galaxy, how much would you get? How much would you get in parsecs? I don't know if anyone has a guess already, or if someone has a calculation handy. If not, I will give you the value later too. I'll leave. Amazing. There's some people that already are giving values 8 kiloparsecs, or Slackshay is giving a more specific value of 7,600, something like that. So that's great. It is. You can remember it as something around 8,000 parsecs or 8 kiloparsecs, and that is the galactocentric distance of the sun. So that is great. Let me close the chat here real quick. So yeah, that is very cool to have in mind. We've been speaking a little bit about the rotation and the movement of the disks, especially of the disk of the Andromeda Galaxy. I don't remember if we showed earlier an image of the galaxy, so this is very nice to have here. This is a very, very cool picture of the Andromeda Galaxy. I want to move this a little bit. Maybe I can show the credits. Yeah. So amateur astronomer Robert Glender in 2002 took this amazing picture, and it's part of the ESA Hubble archive right now, and it's one of the most beautiful shots you can get of the Andromeda Galaxy, or M31, as you will see it a lot. If you want to locate it in the sky, it is, as the name might suggest, it is located in the Andromeda constellation. And if you're in the northern hemisphere, it's easier to see it. Actually, tonight you can try, if you have a clear sky, to go outside and try to spot it. That could be a nice, very fun homework you can take away from these sessions. It's very, very cool. And one of the things I love the most from studying astronomy has been when I have the opportunity to work with data of some object that then I can actually locate in the night sky. This is lovely because Andromeda happens to have an apparent magnitude of 3.1. I don't know if some of the guys that were here yesterday in yesterday's session can tell me, does this mean so it's a little bit more than 3, the value of the magnitude of Andromeda? Can you tell me if you can see that with your naked eye? I don't know if you guys remember from what we spoke yesterday. Can you see, is it possible to see this object with the naked eye if the conditions of the climate, like of the weather, allow it? What do you think, guys think in the chat? Yes, as a couple of you are replying already. Amazing. It is possible. Remember that the limit of our naked eye is actually magnitude 6. So fast, quick reminder that in order to measure or like to have an idea of magnitudes, remember that as it grows, it is fainter, it is harder to see, it is less bright as you go to higher numbers. So 3 point something, it's not super bright, but it is bright enough that even in some cities, if it's not too polluted, or there's not a lot of light pollution, also in some dark spots of cities, you can even see Andromeda Galaxy. I remember back home, and I lived in a pretty big city in Colombia, and in the clearest nights, it was possible to see a faint, like rice grain shaped thing when you go identify Andromeda. As a quick tip, this is I'm deviating a little bit from the galaxy topics, but you can focus on the shape of Andromeda, which is like this little like hockey stick you can think about, is what drives Andromeda. And in this central star on Beta Andromeda, you can go 1 and 2, like you can count like 1 star and then go a little bit higher, and you will see a little rice-shaped thing, which is a little bit hard to see if you have some lights around, but if you go to a dark enough spot, you will see it, and it is really, really nice. So remember, we're working with data from the FAT data set taken with Hubble, with the Hubble Space Telescope, and we have measurements of the velocities of the radial velocities of this disk. I don't know if maybe we want to move forward with notebook 5 before we comment a little bit more on the movement of disks, what we call disk kinematics. Remember this kind of plot that Madeline arrived to. It is really cool, and it allows us to compare. Now, if you see this is like a view of let me move the bar now. In the top, in the title, it says rotation of the stellar disk of the Andromeda Galaxy, and you have this view of a very similar plot of what we got in the last notebook. And you see that this is what we will call like a sky map, or like a on sky plot, because what we plot is the coordinates of the points in the night sky, right ascension and declination, which are just how we locate things in the sky. So this is the location in the sky of the points that we measure the velocity for, or the stars that we measure the velocity for. on Andromeda. So if you compare it with the image that we got previously, so let's see it here. You notice how it allows us to notice how the thing we see in the sky is actually moving, and it's actually like rotating this way. But globally, there is a movement looked at, as Madeline was pointing out, there is a very negative value, you know, there is like mostly negative values that indicate us that this galaxy is actually moving towards us. And it is expected then that in around 4 billion years, there will be a collision, which is what we call a galaxy merger. It is the very, very massive and cataclysmic event of two galaxies mixing up together. So it's very interesting because when you hear the collision of these very, very massive structures, you imagine the apocalypse, you imagine like destruction all around, but it is actually a very graceful dance. You can imagine it like as if it was two fluids mixing between each other. So it's like if you were mixing like milk and coffee, or milk and chocolate, and you see that it's very rare that during this event a collision between stars would happen. Like it's not like the sun is going to be impacted by another star. It could happen, but the likelihood is so low. It's very, very unlikely for this to happen, just because of the sheer scale of the galaxy. The distances between the stars are huge, but yet they collectively hold such a mass that if another huge collection of mass like the Andromeda Galaxy comes close, they start interacting and they start mixing up. So just to close up a little bit this part, we can see this short video that shows actual snapshots. I loved so much this video. It shows like the actual pictures overlaid on simulations of galaxies that we have observed, not that we have simulated to be colliding. So if you were to run a computer simulation where you put a bunch of particles together in the shape of a galaxy interacting in the way that we know galaxies interact, you can start replicating what we observe in nature. So this is an actual real picture. Then we go back to the simulation, and you can see how there is the movement of the galaxies, the rotation that we're studying through the velocity of different stars inside of the galaxy, but there's also a general movement of the whole system. And you have these huge collisions of the two systems blending one into each other, you know, so it's very interesting. And there's another image of another case. And this is a very three-dimensional situation. It's a very three-dimensional event. So we can rotate and have different perspectives. And this is the challenge that when we do astronomy, we face a lot. And it's that things in the night sky look very flat, you know, it looks very 2D. But then you have that when we observe different collisions in the night sky, we are getting a bunch of different perspectives, just that we are not completely sure when we just see it. We're not completely sure what point of view we're getting from the image that we're taking. So these simulations really help us to compare what we know from theory and contrast it with what we see in the night sky. Let's have a view of this one real quick. I didn't manage to make it work very properly to play it. So give me a second that I can reload this presentation real quick, and we can have a quick look at this last video before we move to explore with Philip notebook number 5. So it should be this one. And this is real quick also what I mentioned, a simulation of how visualization of how things will look from the perspective of Earth, of the Andromeda Galaxy approaching us in the following billions of years. So you know that around 4 billion years, there's going to be all this mixture, all this colliding of the two systems that will really, really shatter our night sky landscape. It will really make it very, very different and very weird for someone that could be maybe observing it, which is not going to be any humans, because if you really notice the scale of this event, in the very end, the two galaxies will fuse into this ellipsoidal galaxy. So it's going to be too big. There's too much of a mass for the disks of the galaxies to be stable, to preserve, like to persist in the shape of a disk. It's going to become a more disorganized system, which is what we usually call an ellipsoidal or elliptical galaxy. So this is very interesting, and this will happen in the span of billions of years. So this will exceed actually the lifetime, or like at least the main sequence lifetime of our sun. And definitely it will outlive humanity and probably even life on Earth. So it's very funny that this simulation, just for reference, has these mountains over here in the bottom. But be very sure that those mountains will disappear, will have disappeared long ago. First, because of the geology of Earth, geological times are much faster than these cosmic timescales. But it is just for reference that it was decided to keep those mountains here to just see how the night sky landscape would change if someone was able to persistently observe this event. So yeah, I would like to stop here and maybe continue later with the last little part, short comments on the movement inside of a galaxy, which will be maybe helpful for later.
Thank you, Harold. That was amazing. We have a couple of questions in the chat. Would you like to take them? And then in the
Yes.
meantime, maybe we can take a quick 3-minute break. Is that okay
Perfect.
with everyone? I think we'll still have enough time to go through the rest, right? Okay, cool.
It's perfect. The first
So,
one I see is this one. How long is the actual collision, right? Is the first one?
yes.
Okay. So I'm gonna read it. So Suhas is asking us, how long is the actual collision? Because had actual pictures from telescope. So we have these measurements, like what Raja was mentioning, what Aparajito, Madeline, Philip have been talking about. We have these measurements of the radial velocity. So this is what we call line of sight measurements, because we are very restricted to the flat view of the night sky. You know, it's very hard to see things moving in real time because the scales of that movement, even when the speeds you saw with Madeline, for example, the speeds are in the order of hundreds of kilometers per second. Like if we could travel at that speed in I don't know, like a car or something, we would be zooming, you know, like it would be leaving Earth very quickly. So it is very, very high speeds, but yet the distances are so huge, both the distances that we are trying to measure in the night sky and the distances to those sources are so huge that the movement that we can track is very, very small. Even with that, we have very nice techniques like the spectroscopy. Remember that we were mentioning that you've tried to track the movement of these lines, and with the help of the Doppler effect, you know, the Doppler shift that Madeline was teaching us about, you really can measure very precisely how fast things are moving towards you or away from you. But that's also limited, you know, because you want to know the 3D velocity. You want to know how it's moving towards you, but also you want to know how it's moving up or left, you know, or up or right, or down or right, you know, in this on sky direction. So this really requires other precise measurements and following things throughout the years in the night sky. I think also Raja could also later explain a little bit more in detail about that, because it's not my line of research at all. But I know that there is very, very good ways of throughout the years, and it takes time. You try to really precisely measure the coordinates of things in the night sky, and that is the way that you can really measure. And they have found out that mostly the velocity of Andromeda is towards us. It's like on the z direction, which is the line of sight direction. So this is how they've determined very precisely the shape and the way that this collision is going to happen. And this is how they know that how long is the actual collision. It's around, yeah, in around 8 billion years. So 8,000 million years is going to be, the deal is going to be done. It's going to be mixed very well. Then we have here, Jamin says, how long will it take for the galaxies to fully combine? So it's just what I mentioned. That's the name, which I don't remember what names represent. I don't understand your question, Richard. If you could maybe develop a little bit what you're asking for. I don't remember what exactly I was saying when you said it. How galaxy collisions differ from supermassive black hole merging. This could be a topic that we could discuss further in the Slack. Mainly, I want to comment that, yeah, it's, when you talk about black holes merging, this is a very, very energetic and cataclysmic event that is very concentrated in a very localized in space and time. So you would track that thanks to following gravitational waves. but that is another topic. Instead, galaxy collision is something that we can follow in a larger scale, and it takes way, way longer. What happens to the supermassive black holes in the center of the Milky Way and Andromeda? This is definitely a question for someone that knows more about galaxies than me. We can discuss it further also in the Slack. I don't want to deviate too much without having the right sources for this. So please, Vedant, bring this question to the Slack. It will be lovely to have that discussion over there. Sure, wanted to mention the Sinba repository of star catalogs. It's very, very nice. I agree. If you want to follow very precise or very reliable measurements of different star properties, you can go to Sinbad from the CDS hosted by University of Strasbourg here in France. So that's very useful. I think that's all we have for now, right?
Yes.
I think so, yeah. Perfect.
I think those are all the questions. Thank you so much, Hirval. We will move on to our very last notebook and the very last segment of PyaR 2024B. Philip, I believe you'll be covering this one.
Actually, there are two more notebooks, right? It's 5 and 6.
Yes.
Yes. And I think,
right.
there's something in between them as well.
Yes. Yes.
Yeah.
5 and 6.
So exactly. So I'll try to do 5 a little quickly. I'll be done in about 20 minutes or so. The hero, you can sort of do the next part, and then I'll come back and do the last one.
Yes.
Oh, I'm not allowed to share my screen. I think I left the meeting by accident. So can you just make me co-host as well? Brilliant. Thank you.
Definitely, it's working now.
Yeah, perfect.
Okay,
Just
perfect.
a second. Just going to share my screen right now. Yes. Can everyone see my screen? Yep. Perfect. Fantastic. Okay, guys. So we're now going to move on to activity 5. And this is the simulated disk activity. And right, so let's start off. There's not actually much to do in this notebook, so there aren't as many exercises like in the previous notebook. So you'll have to basically, the notebook that you have got, you could actually run it completely and you'd see what it gives you. So I'm going to walk you through the text that we're running here. And then the next notebook, we're actually going to do something similar with real data. Okay. So what we're going to do is we're going to simulate a disk of Andromeda with a large number of stars. Okay, we're going to simulate them, and we're going to see, how we can calculate different quantities out of this. In order to simulate this, Raja and Claire and other people involved in the program have created for us a package, a small Python package called fake disk, which creates a fake disk. Now, you'll actually find this package inside your folder. So I'm just going to show you what that looks like. So if you open your folder here, you should see that there's a fake disk.py file down here. I'm just going to open this file, and you should already be able to see that it looks very different from the other files here. All of these other files are IPYNB, meaning that these are interactive Python notebooks. But this is a .py file. It's a sort of older Python file. And it's going to, once you open it, you're going to see that it looks very different from all the other notebooks that you've seen so far. This is not a notebook in the same way. And it has a lot of text and a lot of code in it. You don't have to touch this. You're not going to edit this. I'm just showing it to you here just to tell you that this is where all the code is. If you'd like to go in and see what it does later, you can do that. But we're not going to use any of this code directly. What we're going to do is we're going to call it. We're going to import this as a package into the activity 5. And we're going to import it using this line here that says from fake disk, that is the file fake disk, import fake disk. Okay, and now we will be able to use any of the functions that have been defined inside the fake disk Python file, and we can use that here. This is a very useful thing because you at some point you'll start writing certain functions that you might think are very useful functions, and you might want to keep reusing them. And if you want to do this, it would be very nice to put all of those functions inside a .py file, and then just keep calling that .py file again and again in different files so that you can use all of these useful functions. So that's exactly what Python packages do, except these are huge packages that are bundled up and placed online somewhere. So this is a small Python file that someone has created for us exactly for this activity. So we import that, and we also import our standard Python matplotlib and numpy packages. So I'm just going to run this cell to make sure everything's imported. And then I'm going to walk you through this particular function here. So you've already seen what a function is. So it's a bit of code that we sort of chunk together and place inside a single block, so that if we ever want to call all of these pieces of code together, we can just say show map, which is the name of this function, and put in some parameters, and it'll produce whatever this code, it'll reproduce everything that's inside this particular function. So what does this function do? So this function will create a color map for us. It'll create a plot for us, okay? Now it accepts a bunch of different quantities here, which I will explain a little further down. But once it does this, it creates a plot axis with equal aspect ratio. It sets the labels of the plot. On the x-axis, it sets the word psi. We've already seen that this is a coordinate. We've already talked about this in previous notebooks. On the y-axis, it labels it to be eta, another coordinate. It gives a title, say simulation. And then it sets the x limit of the graph. In other words, it sets the lower value of the x-axis and the upper value of the x-axis. And then there's an input parameter called cutoff, which is false by default. This is a Boolean variable. And if cutout is true, or in other words, if cutout, then what it will actually do is it won't plot the entire graph that you're going to ask it to plot. It's just going to plot a sort of quarter section of this. And then once all of this is done, it's going to take the quantities that we're sending in. So we're sending in something called sim, which is a simulated disk, which we're going to talk about a little bit later. And it's going to scatter the x coordinates on the x-axis and the z coordinates on the y-axis. Now, this might be a little confusing. That's because in this tutorial, we're going to use an xz plane. We're going to use the x-axis along x coordinates on the x-axis. And then we're going to talk about the z coordinates that are perpendicular to it. If you're more comfortable, you could use something called y, but this fake disk function gives you values that are x and z. So we're going to use x and z for that. So this is a scatter plot with x coordinates and against y coordinates. So these are the coordinates of the different stars inside our fake disk. And we're going to set a color, just like we've done in the previous notebook. And this color is going to be whatever I set in here as the quantity. Now, in the previous notebook, you would have noticed that the quantity that was being sent in was the velocity of these graphs, right? But in this particular notebook, the quantity that's going to be sent in is going to be something different. We'll talk about that in a second. It's going to do with the standard deviation of these of the velocities of these stars. So we're going to create something called a dispersion map. Then you can set the size of the scatter points to be 2 units. And just as in the previous notebooks, you can also set the lower and the upper limit of the color map as being Vmin and Vmax that we're setting up here as default variables. Notice that Vmin and Vmax in the previous notebook were the cutoffs for the color map in velocity. Over here, they're not really the cutoffs for velocity. They are whatever the quantity is that we're sending it. They are the lowest and the highest values of that quantity that will show up in the color. So when I run this, nothing's going to happen. It's just going to create, it's just going to define the function. And we're going to use this once we create our disk. So we're going to create our disk here, and we're going to do it by calling the program fake disk that we've imported up top here, okay? So before we do that, we need to define some parameters, which I'll describe in a second. One of them is called the scale factor. The other is called the dispersion. There's an inclination angle, a position angle, a rotation velocity, and a number of stars, n. And we send in all of these different parameters into the fake disk function, like so. You set n to be n, you set the inclination angle to be inclination. Remember, fake disk accepts all of these different variables as parameters, and it will create a disk based on this. So now let's actually go through these different parameters. Let's start from the bottom and start moving up top. So n is clearly the number of stars in our disk. We're modeling a fake disk for Andromeda. So in this case, we're just taking 10,000 stars. A nice thing that I like to notice here is that, so in Python, I have trouble, for example, knowing how many zeros I've typed out here, so I occasionally make a mistake. So one nice thing about the newer versions of Python is that you can put an underscore, and this underscore works almost like a comma, which means that you can separate different numbers of zeros, and that will make it easier to read. So right now we've got 10,000 stars in our disk. And then we have a rotation velocity for our disk. So we have the disk of Andromeda, which is rotating, and this will tell you the velocity of rotation of this disk. Okay? And then we have two different angles here, one of which is called the inclination angle, and the second is called the position angle. And this is the orientation of this disk in the sky with respect to us. And I'll talk about this a little bit more once I've actually plotted out the graph. Then we have two more parameters, the scale factor and the dispersion. I'll come back to these later, but they are required right now to create the fake disk. So when I run this, it's going to create a fake disk and put it in this parameter that we're calling sim. In the meantime, I'm just going to add line numbers. Yeah. Great. So now we have a fake disk of Andromeda, and we have a simulation that that stores all of this data. And now we're going to use this down here to do a plot. Okay, so you remember the showmax function which we defined up here. So we're going to send in the simulation sim. Okay, and we're going to send in sim, and we're going to plot the quantity that we're going to give, the color that we're going to get over here is the y velocity of every star in the disk. So we're going to take in the stars of the disk. We're going to plot their x and z coordinates on the axes. And then we're going to set the color of each of these points to be the radial velocity, the velocity along the y-axis, which is in kilometers per second. So I'm just going to run this right now. And Vmax, of course, is our maximum color bar value. So I'm going to run this. And down here, you should all be able to see that we have a simple color map, very similar to what we saw in the previous notebook, at least in spirit. And you see that there are many, many different points here. Okay, and the number of points that are here is governed by the parameter n, which in this case is 10,000. Okay, and so you have the x coordinates over here, which is psi, the z coordinates in this case, which is the eta, and then we have at each point a different color, which indicates a different radial velocity along your line of sight of a star that's placed here. So this, let me ask a question in the chat. Let's see how many people can answer this. In which way do you think the disk is rotating? Do you think it's rotating clockwise, or do you think it's rotating anti-clockwise? Does anyone want to try and answer that on the chat? Just going to take a look at the chat in case it's open. Okay, someone seems to have already said that the spiral arms. Oh no, that's a previous note. Is anyone able to answer it? Okay. If no one can, then basically what you need to do is you need to look at which color is positive and which color is negative. So the color up top here is bright yellow, and it's a positive velocity of around 200 kilometers per second. And you see that the top part of the disk is positive. And so positive velocity is when you're going away from us, and negative velocity is when you're coming towards us. So this disk is rotating in the direction that my mouse is moving. So this is a disk that rotates clockwise, I suppose, in this case. Okay. Now, let's look at what changing the different parameters does. So for example, if instead of 10,000, I ran 50,000 stars, then this might take a little longer to generate, but you'll see that I have a larger number of stars here. And so you can see the variation in the colors much clearer. Okay? You see a lot more points. Okay. Now these two coordinates, these two angles here, the inclination angle and the position angle, are going to tell us why we actually see a disk in the sky. So the reason for this is that the Andromeda galaxy, like you've seen in some of the photos, these different galaxies that we look at, they're sort of like frisbees, right? So if you're looking at them face on, in other words, you just look at them like completely face on, they would look like a circle, right? But now what you need to do is you need to realize that this is a frisbee, and if this frisbee is even slightly tilted, the circle is going to look like an ellipse. Okay, and so that's why we actually see an ellipse, because it's a tilted frisbee. Now, how it's tilted, the way there are two ways in which there are two things that you need to define in order to orient this frisbee in the sky. And one of them is called the position angle. And the position angle is the axis about which this frisbee is being tilted. And right now, the axis is actually around from the top right to the bottom, sorry, the top left to the bottom right of this image here. So that's the axis about which this disk is going to get tilted. And the amount by which it's tilted is called the inclination angle. So both of these things uniquely define the orientation of the disk in the sky. Okay, so that's what these two parameters give us. The last parameter that gives us that we're going to use is the dispersion, and this is called the velocity dispersion. So if you'll notice, if you look down at this graph here, you see that most of the points in this region do seem to have a velocity of greater than 200 kilometers per second. But there are a couple of points somewhere down here, for example, that you see that it's not a homogeneous yellow band, right? So there are actually, it looks a little like salt and pepper, like this noise around here. And that's because the velocities are not all exactly the same. There's some amount of randomness that's been introduced to this velocity. And the amount of randomness that's been introduced is given by this factor, which is the dispersion. So if I set this factor to 0 and I run this particular cell, you'll notice, and I'm just going to rerun this cell again, you're going to notice that the disk does not look like it has any dispersion at all. Every place seems to have a homogeneous color. But if we now start increasing the dispersion to say 100 again, you see that it becomes a little bit more noisy. There are different values, sometimes 200, sometimes something less than 200. There's a large amount of dispersion here. So this is the amount of dispersion about the actual value that that point would have, right? Now, when I make this number comparable to the rotation speed, so the rotation speed is 200, and when I make this number comparable to the rotation speed of around 200, that means that at any given point, you can have a very large dispersion. You see that it becomes much more sort of random at this point. If I make this even higher, say around 1000, massive dispersion, then you'll see that there's almost no sense of rotation over here, because at every point, there's a large amount of random noise attached to that point. And so you can't even see that the disk is rotating. So we're going to stick with the value of 100 right now. And that's going to produce this particular type of disk. But remember, this is just the velocity plot. So this is a very similar plot to the one that was shown to you in the previous notebook. What we're going to do right now is actually try to quantify the amount of this dispersion at every point. Okay, now how are we going to do this? We're going to do this by going to every single star, and we're going to look in a region, in a circular region around that star that's about 200 arc seconds large, like a radius of around 200 arc seconds. Okay, we're going to find this region, and we're going to say, okay, what is the range of dispersion within this circle? Okay, and I'm going to find the amount of dispersion within the circle using a metric called the standard deviation that Hiro will be describing, I think, in the next in his presentation just immediately after this. Okay, and then we're going to plot, instead of plotting the radial velocity at each of these points, we're going to plot the value of this dispersion within this circle in this for every point, and use that as the color. Okay, so in order to do that, we need to first define a circle, right? A region of sky over which we're going to be doing the average. So over here, we're generating a dispersion map using a 200 arc second smoothing circle. So we're going to read around every star. We're going to look at 200 arc seconds around it. And we're going to use all the stars within that region and find out the maximum dispersion of the stars within this region. We've already seen in the previous notebook that 1 degree was 13.67 kiloparsecs. So we need to actually move from this 200 arc seconds to a unit of distance, the kiloparsecs. And since 1 degree is 13.67 kiloparsecs, and 1 degree has 3600 arc seconds in it, because there's 60 arc minutes and 60 arc seconds in every minute, then we just have to divide this number by 3600 to go from arc seconds to kiloparsecs. And then we have a couple of empty arrays here that have as many elements as there are stars in our disk. Okay, so there's sigma and there's SV. And then we're going to define our smoothing circle, which is going to be 200 arc seconds, but converted to kiloparsecs. And then what we're doing in this line is that we're looping over every star in our disk, and we're calculating both sigma and sig SV by using a function that is predefined within our disk. In the next notebook, I think we're going to actually write a function that does pretty much this for observed data. But right now, this function will actually give us the value of the standard deviation, which again is a concept that we'll learn about soon, which tells you how much of a deviation in velocity exists about every point in a circle that's 200 arc seconds large. So when I produce this, you're going to see, when I run this, you're going to see that it produces a disk. There we go. And you can see that it produces a disk over here. And what's the average value roughly on this disk? If you look very carefully, you should be able to see that on an average, the value of the dispersion is around 100. There are some variations about this, and that's to do with the fact that sometimes you have values that are slightly above 100, sometimes you have values that are slightly below 100, but you have these little circles of 200 arc seconds, and you're averaging, and you're looking within that circle for the range of dispersions. And this tells us that this particular disk has a more or less constant velocity dispersion of around 100 kilometers per second, but there are, of course, slight variations in the patterns here. And this, as you can see, depends very strongly on the size of the smoothing circle. So if you made the smoothing circle really, really small, say around 20 arc seconds, what would then happen is, there'll be a little bit of issues with this, and it'll take a little bit of time to run, but you will notice that the entire velocity dispersion seems to be really, really small, close to zero. And that's because there's almost no space around every star. You're taking a star, you're taking a small region around that star, and there really aren't many stars in that region. And so the standard deviation, or the range of possible velocity values within that region is going to be very small. And so you've got almost a constant value of roughly zero. And so we can't really use this to diagnose anything in our disk. On the other hand, if we use a smoothing circle that's too large, say around 200 arc seconds, which I think would be roughly the size of Andromeda in the sky, maybe a little larger than that, then we've chosen a smoothing circle that's so large, it's larger than the entire galaxy, that we're going to get more or less a constant value, again, of a much higher, like over here you see a much higher range, and over here you see, you can't really tell about variations within the disk. So this is not going to help us. So 200 is around the right value. Okay? And we can see that we get a graph of the dispersion on the disk of the Andromeda galaxy. Okay. And now in the next notebook, we're going to actually try and look at the velocity dispersion of the different stars that we've looked at in the previous notebook, using the different catalogs. So I can just run this last cell, which just plots the radial velocity over a small cutout. But I don't think I'll do that right now because we're running out of time. And I think we can move on to Hero's astrophysics background section. That's okay.
Thank you so much, Philip. That was amazing. If anybody has any questions, please post them to the Slack. Or you can post it to the chat for now. I can read them out while it gets set up. This is going to be the last astrophysics background section for the day. This is the second to last section. Yeah, if nobody has any questions about the previous section, I guess we can go ahead and get started with this one. Carol, take it away.
Okay. Let's share. Let's see if it's working. Is it visible? Hopefully. Perfect.
Yeah,
okay.
So
it's gonna be really quick. Just a couple of comments that could add on top of what Philip was already mentioning, what we've been trying to repeat a little bit about the movement of stars and how we measure it and why is it relevant in the study of galaxies too. So remember, there is a very interesting thing. Let's move this bar down here so it doesn't, it lets us read. There's something very interesting that happens with galaxies, and it happens with many rotating objects, and is that they present something that we call differential rotation. So this means that galaxies, as we mentioned earlier, behave a little bit like fluids. If you see their grand scale movement, if you see them in the grand scheme of things, they don't move like a disc, like for example, if you have a little frisbee. I really love the frisbee analogy that Raja was doing earlier, but the individual rotation, when you try to see it, it's not exactly like a solid frisbee rotating. It's actually more like a fluid that rotates at different rates depending on how far you are from the center. And this is very, very important because it has been determinant to the way that we understand galaxies nowadays. The sun is in a more inner orbit, like the one that we see in the center here. And then there is other stars that are in more outer orbits. Our intuition, for example, thinking about the solar system, is that more inner orbits are going to be faster than orbits on the outside, because in the solar system we have a very compact object in the center that is ruling the gravity around us, and this determines the movement of everything to be what we call Keplerian. We have the Keplerian movements, which is the movement in systems that are governed by a central big mass. But here the mass is distributed along a huge area, like a huge structure, which is the whole galaxy. And this makes that this Keplerian way of seeing orbits doesn't work anymore. And now we have something that we call differential rotation, and the rates are not exactly what we expect. What we have actually observed, which we can check out right here, is that in this plot, similar to the plot that we're working on, we have the rotation, at least we can kind of see it. The rotation really gets high when you're towards the edges of the disk. We can see this better if we think about something that astronomers call galaxy rotation curves. This might be a kind of weird plot, but don't get too scared about it. The important part is that this top curve that we see here that says observed is what we notice from stars. When we go outside of the when we start going like farther away from the center, we see that towards the center is like actually slower velocities, slower rotation velocities, and then it like peaks at some point, but then it stalls and then it goes like lower. And this actually defied the way that even taking into account the differential velocity of the way we saw the galaxy before. So it would be the expected curve that we see here in the middle. This is the expected differential rotation that we would expect literally from a disk galaxy, like from a spiral galaxy. But then we observed something higher. And this led to a very huge breakthrough in astrophysics and in physics in general, which was the proposal of dark matter, the existence of dark matter. So this is very, very interesting. This was noted very importantly by Professor Vera Rubin. In her work, she noted this rotation curves problem. And this is what led this led to the fact that nowadays the consensus, this is not a solved issue, but the consensus seems to be that, okay, there is some contribution that we see from the normal disk, the distribution in a disk-like shape that we see from the gas and the dust and the stars, but then there's also like a bulge structure that can also be seen by telescope. We can see it in our own galaxy and in other galaxies. We see both the disk and the bulge, which is like a more spherical distribution around the center of the galaxy. But just accounting for this too gives this expected curve. And then when we measure the actual velocities, we see how they persist in being very high. It kind of stabilizes as you go outside. And there should be some extra matter that is there motivating this motion. So this is very important. And this is just on the surface, just very conceptual for you guys to have some idea of what we talk about, or why is it useful to measure also the velocity to which these stars inside of a galaxy are moving. So this is very interesting. This is the end of this part. As I mentioned, it was like fairly quick. A quick comment. There is this very important concept that also Philip was mentioning a little bit, and it's like depending on the stars that you're observing on a region of a galaxy and just the specific properties of the galaxy, there could be a big spread around the values of velocity that you find. Maybe on this tail of this galaxy, of this like further away distances, you might see maybe not all the stars are around the same speed. This might be their average speed, would be like this 1.2 value that you see here. That is arbitrary velocity units. It's just some value that they use for the model. But you can have a huge dispersion around it, and how compact that dispersion is exactly what he was mentioning to be the standard deviation of the velocity distribution. So this is an important concept that we're gonna keep hearing about. If you start working with data sets that have lots of measurements, that you have a spread of, for example, in this case, velocities, but you will see that if you see brightnesses of stars, temperatures of stars, masses, all of these different quantities that we mentioned yesterday are going to keep showing up, and they're going to show up in huge bulk numbers. We're going to see them by tons. So this is very important to point out, because there's these kinds of statistical ideas like standard deviation or distributions that are going to keep popping up when we do data analysis. So yeah, this was just the short context that I wanted to give back for the ending of the astrophysical context. So the takeaway is a disk like a galactic disk will not rotate exactly like a frisbee. There is some in the velocity of the stars, depending on where they are. That is not exactly what we would expect, either from it being like a solid disk or it being something similar to our solar system. It is a totally different thing from what we usually see of rotation of things in physical systems. So it is a very, very interesting fact that is connected both with the way that the galaxies move, but also with how their structure can be very, very heavily composed by something that we cannot even directly see through light, like is dark matter, which can be a little bit of a matter of debate, but it's a very interesting thing to take into account. There is a visible effect of something that we don't exactly understand how it works, but it's there.
Thank you, Harold. Can you quickly please share the slide with the velocity distribution of the stars in Andromeda? I quickly want to point out something, because that shape is something that all the participants have been seeing. The one
Yes.
before this one.
Yes, give me a sec. I
Yes.
find it. So it's this one.
Yes, that's the one. So this is a shape that we have been seeing throughout this tutorial. And I just want to point out what exactly this is. This is mostly the top half of Andromeda, of the Andromeda disk as we see it from the Earth, all right? And if you go over to page 4 of the paper, of Claire's paper, the paper that this entire tutorial is based on, you will see an image of the Andromeda with purple and white bricks, rectangles, overlaid onto it. And the white rectangles that are overlaid onto it, they cover the entire area that was mapped for this to create these images. Okay, that's the survey data that we have been using. So the orange bit that you see here is basically the northern half of Andromeda. The purple bit that you see here is part of the southern, but not the tip, only close to the center. And the bulge is mostly left out. That's why there's kind of a void there in the middle. Near, say, 145, above, near, say, between 150 and 140 on the x-axis, and between 670 and 680 on the y-axis. That void is basically where the center goes. So that's what you're looking at if you want to compare the simulation that Philip created with Notebook 5 with all the data, all the plots that Philip will generate with Notebook 6. That's how you should interpret it. And with that, I will pass it on to Philip for the final notebook. Thank you, Harold, for that amazing segment. And with everybody, if you have any questions, you can post it to the Slack. I will share the Slack one last time.
Shall I start then?
Yes, Philip, please.
Okay. So we're going to start the last activity of this workshop, which is, and just before I go into that, I'm just going to add a little bit more to what Hero said earlier about standard deviations and distributions. So what I'm going to do is I've just Googled this quickly. And over here, if you just Google standard deviation, you get a Wikipedia article, you see this graph. And what happens here is if we ever have data that you assume to be distributed along a bell curve, like this one over here, right? then there is a sort of natural unit in which to measure the spread of a particular bell curve, and that is called the standard deviation of the bell curve. Now, there's a mathematical way of computing it, which I'm not going to go into right now. But what this basically says is that between 1 sigma on the left and 1 sigma on the right, you have about 68.2% of the data. And so this sigma is a sort of unit of the spread of a particular bell curve, like how wide this bell curve is, because you can have different bell curves. So for example, I've just Googled standard deviation, and you see this on the right-hand side over here, you see 2 different bell curves. So both these bell curves have the same average. So they have the same value mu for their average. But you see that this particular bell curve has a lower standard deviation than this one. And therefore, there is a larger dispersion in the values for the bell curve that's given on the top here than for the bell curve that's here. So this is a bell curve with a much lower dispersion. And we're going to use this notion of standard deviation to actually measure the dispersion in small regions of space, just like we did in the previous notebook, but with actual real data. Okay? And we're going to do this we're going to create these sort of dispersion maps, very much like we created in the fake disk activity just before this. But we're going to do it for the 3 types of stars that we've seen in this week. So there's the main sequence stars that you saw in notebook 3, the red giant branch and the asymptotic giant branch. And now what we have, what you would need to make sure that you have is run everything in notebook 3, because we're going to use these 3 things, the RGB catalog, the AGB catalog, and the MS catalog. So if you haven't run it, you should go back and open that notebook and run these things so that you can get these 3 catalogs, because otherwise a little bit later on, you're going to have trouble. If you can't do that right now, it's perfectly fine. Just you will probably have the MS catalog already, and then you will get one set of results, and then maybe in your own time, you can go back and do the other as well. So let's go back to this activity right now. And the first 2 cells are very similar to the previous notebook that we saw. We're importing a bunch of packages. We're not importing fake disk because we don't want to create a fake disk. We're actually using real data in this section. And then we're going to define our show map function exactly like we did before. We have a xi and an eta, which are the coordinates of that we're going to plot. A quantity, which is going to give us the color of every different point. Xi and eta are the coordinates of the different stars, and the quantity will be the color of each of these stars. And then we have a label and a file name in case we want to create this file somewhere, which we will be doing. Okay. And that's done by this line here, which is the plt.savefig, which takes whatever figure you have and saves it to a specific file in your computer. Okay, so this is not something that you need to think too much about. You don't need to add too much to this because it's exactly like what we've seen before. But now comes, in some sense, the hardest part of this entire tutorial. And it will combine a bunch of different ideas that we've seen in all of these tutorials. And what we're going to do is we're actually going to go ahead and calculate the dispersion. Now, in the previous notebook, we didn't really calculate it. We just got the dispersion sort of pre-calculated for us using the simulation.getSV, I think, or something like that, sort of this function that means. We're actually going to get the dispersion now using this. Okay? So we're going to do that by defining a function called getDispersion. Right? This is our function. We've defined it. It takes a bunch of x coordinates and z coordinates. It takes a velocity. So these 3 objects are arrays, with every element being the value for a specific star. So the first element of x, the first element of z, and the first element of v would be the x coordinate, the z coordinate, and the velocity along the line of sight for that particular star. And then we have a circle size, which we've already described earlier, which is the region over which we want to look at all the stars. So essentially what we want to do is we want to take a specific star and we want to look at a region of around 300 arc seconds around that star, right? And we're going to try and find the dispersion in that region in the velocity. In other words, what if we assume the velocity to be distributed in a bell curve like this, what would be this region, the range of dispersion within this region? Okay, so we're going to start off by defining an array. Just a second, let me get my line numbers on. There we go. We're going to start off by defining an array of zeros over here. With how many elements? Well, as many elements as there are stars, and there are as many stars as there are coordinates in x or z or v. And so over here, we define an array of zeros called dispersion. And so now what we want to do is for every one of these stars, we want to take out all the other stars that are less than 300 arc seconds away from the star. And then from those stars, I'm going to take the standard deviation of the velocities of the stars inside that region. So I just want to make sure that everybody understands this, because this is a slightly complicated concept. So I just want to make sure I'm going to repeat it again. What we're going to do is we have a list of stars. We're going to take every one of those stars. We're going to look around it to find all the other stars that are less than 300 arc seconds away from that star. And then we're going to find the range of velocities by looking at the standard deviation of the velocities of all the stars that are inside that region. So in order to do that, what I first do is I loop over every star. So that's what I'm doing in this case. You remember what we've done with loops. So I say for I in range 0 to the length. So if there were 10,000 stars, then it would run from 0 to 9,999. So for every one of these stars, I get its x coordinate and I get its z coordinate, and I store it in the variable this x and this z. Okay, great. So this is very simple so far. So I've got the coordinate of a specific star, and these are coordinates, of course, in angles. So now what I need to do is find all the other stars that are a distance less than 300 arc seconds from this. Okay, and in order to do that, we're going to calculate an array of distances of every other star in Andromeda that we have, in the catalog of Andromeda that we have. And I'm going to calculate the distance from this specific star. And the way that we do this, I'm just going to create a new cell here. The way that we do this is by using the Pythagoras distance formula. So what would we do? The distance d is equal to, so if I have a specific location x0, then the distance between any point x and x0 is x minus x0 square plus y minus y0 square. And I take the entire thing and I do a square root around it. Right? So what I'm going to get, oops, is this right now? I need to proceed. So I'm going to find the distance of every point of every star that has a specific x and y coordinate. And oh, sorry, in this case, it's z. So let me just write z to avoid confusion. So every point x and z, I'm going to find its distance in the x coordinate from that particular star x0, and the distance in the y coordinate from that particular, from the z coordinate from that particular star z0, square it, add it, and then take the square root of these two quantities. Okay, this is the standard distance. Now, ideally, I mean, what you might be tempted to do if you have some familiarity with other programming languages is to put another for loop here that loops over all the other stars, excluding this star, right? And then calculates the distance. But it turns out that with NumPy arrays, we can do things very, very simply, because you've seen that we can use NumPy arrays like vectors. And so what we could do is we could just do this x minus, sorry, we could just do x minus this x. And I'm just going to explain why this particular thing works and what this particular thing is doing. So let's say I had a NumPy array, which was given by, for example, the following numbers: 1, 2, 5, 8, 23, 100. Okay, so I have a list of different numbers here: 1, 2, 5, 8, 23, and 100. And if I just print my array now, it's just going to print out all of these different numbers. And now let's say I subtract a constant number from this. Let's say I subtract the number, say, 1 from all of this. So NumPy is intelligent enough to say that if you take an array and you subtract a constant number 1 from it, what you mean is that you want the number 1 to be subtracted from every one of these elements. So let me just print the array here, and underneath it, let me print the array minus 1. And when I run that, you'll see that 1 goes to 1 minus 1, which is 0, 2 goes to 2 minus 1, which is 1, 5 goes to 4, 8 goes to 7, and so on. So if I subtracted the number 100, it would subtract the number 100 from every one of these numbers here, right? So what I've done here is I've taken a list of positions, an array of positions, x, and from every one of these elements, I have subtracted a specific point, a specific coordinate that is this particular star's coordinate. Now, if I square this, NumPy is intelligent enough again to square every element of that array. So let me go back now to make this array -1, and then let me square the array -1. And if I do that, remember, if you square it, to square it, you have to just do a star, star, and 2. That means raise it to the power 2. And then what you see is that 0 is squared to 0, 1 is squared to 1, 4 is squared to 16, 7 is squared to 49, and so on. So this particular line takes every star in our list of stars, subtracts the coordinate of the specific star that we're looping over, and squares it. Then we do exactly the same thing for all the z coordinates. Square it. And then we do the square root of this by using the np.square root function. So over here we have dist, which happens to be an array of distances, just like something like this, an array of different distances over here. Okay. And now what we're interested in is finding, so this is an array of distances of all the stars in Andromeda away from star number I. Okay, and now what we want to do is we want to just pick out those values from this that happen to be less than 300 arc seconds, which is a number that has been defined by circle size. Okay, so I can do that by creating a mask, and this is a mask. So we're going to do that here. I'm just going to say creating a mask of stars to keep. Okay, and I do that by saying I want all stars whose distance is less than circle size, right? So this will return a mask, which is a bunch of true or false values, which will be true if we want to keep the star and false if we want to reject the star. And now I can just define a new variable. So for example, velocities to keep, which is just the velocity array with the mask applied to it. So that I'm just going to run down another cell here just to give an example of what this means. So just as before, we had our array, which was this. Let's say I wanted to find out all the elements that had values less than 8. So if I printed out array less than 8, I would only get the values 1, 2, 5 as being true, and the other values as being false. And indeed, if you see this, you see that you get true, 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 because the first 3 values are less than 8. And then 8 is not less than 8, 23 is not less than 8, and 100 is not less than 8. And now if I put this entire thing in square brackets, if I say array, wherever array is less than 8, we've seen this before with masks, what it's going to do is it's only going to return those values of the array that happen to be less than 8. Only those values where this mask happens to be true. And if I run this, you'll see that I get 1, 2, and 5. Similarly, if I said greater than 8, it will give all values like 23 and 100 in this particular cell. So we've basically filtered out all of the different variables, from the entire array, we've filtered out those points that we're interested in. And in our case, we want to filter out the velocities of only those stars that happen to be a distance circle size away from this specific star. Okay. And now I just need to calculate the standard deviation of all of these velocities. And that's easy to do by using an inbuilt function called np.std of velocities, right? And so this will then store the dispersion about star number I. And then we go on to the next one. So we start off with star number 0. It finds the dispersion in a 300 arc second radius around star number 0. Then we repeat this for star 1, for star 2, and so on. So I just run this. And of course, nothing's going to print out because this just defines the function. But now all we have to do is actually calculate what these values, what the dispersions are for the different stars that we have in our different catalogs. Okay? And so these were the catalogs that we created at the end of notebook 3, I think. There's one for the main sequence. So over here, we're going to read the data for the main sequence stars. But remember, we don't care about everything. All we care about are the coordinates, the xi and eta positions of the star, and its velocity. So we're going to use the numpy.loadText function, just like we did before. From this particular file, we're going to unpack it into each of these different variables, but we're only going to use the columns that are xi, eta, and v. So we're only going to use these 3 columns, 2, 3, and 6. Now, this set of code you should not ignore. This is a very important set of code from 4 to 11, but it's not something that's important for us right now. It just basically means that there are certain values of stars in this catalog that happen to have velocities that are much greater than 1,000 kilometers per second. And often this is a sign that they aren't actually part of the Andromeda galaxy. And so we're going to actually clean our catalog by removing these stars from the catalog. Okay, and we do that in exactly the same way that we did before. We define a mask that keeps those values where this velocity, the speed, or rather the speed, is only less than 1,000 kilometers per second, and only take those values which are less than this. And then we just calculate the dispersion using the get dispersion function that we've defined above here.
By the way,
And then we
Philip, you have 5 minutes.
Fantastic. I'll just finish this off right there. Thank you. So, and then I'm going to just show the map down here, and it's going to save the file in this particular folder. Okay. So I'm just going to run this, and you should say, oops, there's a problem because it says mask is not defined. Oh, I'm sorry. I made a mistake here. This should not be mask. This should be keep, right? Because keep is what my mask is, right? And there we have it. We have the dispersion of the main sequence stars in the disk of Andromeda. You see that the main sequence stars are present all over the disk, more or less in different regions. But the average color that we see in this graph is blue, is a sort of darkish blue, meaning that the velocity dispersion of the real data of main sequence stars is relatively low. In other words, main sequence stars have a relatively low velocity dispersion. Very few of them, maybe a couple over here, a couple over here, have a high velocity dispersion of 160. And now what we would like to do is do exactly the same thing for the AGN stars, AGB stars, okay? And all we have to change is change the catalog. Instead of the MS catalog, we use the AGB catalog. Everything else is exactly the same. And we change this to say AGB sigma. And then we show a color map with AGB sigma here. And we change this name here to AGB dispersion map. And if we now run this, you should see that the AGB stars show a little bit more of a dispersion. You don't see that many of the low dispersion stars or that many of the high dispersion ones. The majority of them are somewhere in between these two. And now I'm going to leave it to you. I'm just going to do it very quickly. I'm going to do it for the RGB stars. Oops. And I just need to make this an RGB catalog. I just need to change this to RGB sigma and change this to RGB sigma here. And then I'm going to plot the graph for the RGB stars. And what you should be able to see here is that the RGB stars seem to have a much higher velocity dispersion. And this, I think, is one of the results of the paper, that you have the main sequence stars to have a very low velocity dispersion, the AGB stars to have an intermediate velocity dispersion between main sequence and RGB, and the RGB stars to have a very high velocity dispersion graph. Okay. Now, there's another way to just quickly visualize this in 2 minutes, is to actually plot the distribution. In other words, the curve of a histogram of all of these different values of sigma. I don't think I'm going to do it in great detail here. I think you can go over the solved notebook and you can work that out there. But this is just to say that you could also look at how these different stars are distributed. The velocities of these different stars are distributed. So I'm just going to see if I can very, very quickly put in a histogram by just saying plt.hist of, say, ms sigma. And I'm just going to plot a histogram of ms sigma with a label saying ms. And I'm just going to put the color as being blue because it's blue. And I'm going to say density equals true. And if I run this, you see that I get a histogram of different values for the main sequence stars. And you see that this histogram is sort of peaked around 60 kilometers per second because that's what the x-axis is over here. It's in kilometers per second. I'm just going to write that down at the x-axis down here. Just a second. Then I'll be done. There. And now I can do exactly the same thing for the AGB and the RGB stars, and then I'll be done. Stars, and I'm going to change their color. AGB is green, RGB is R. And now when I run this, you see that the main sequence stars have a value that's peaked around 60. The RGB stars have a much higher value, peaked around 110 or so kilometers per second. And the AGB stars have a spread between both these. So we see that at least between the main sequence and the RGB, the velocity dispersions are very, very clear. So these two stars exist not only in different regions of the Hertzsprung Russell diagram, they also seem to have very different velocity dispersions, meaning that they probably had a very different history during their lifetimes. So that I think would be the end of this notebook. The last bit is a little confusing, but really what you should be focusing on is the lines down here between lines 12 to 21. And you should see that what we've done here is actually very complicated, but it's really, really compact, and we can do a huge amount of stuff. And this just shows the power of Python, where you can do this very complicated thing in a very simple way. So feel free to ask me any questions if you're confused about something here. We'll also be on the chat on Slack, so please feel free to ask questions over there as well. And I hope this was clear. Okay,
Thank you,
so
Philip.
I'm just going to stop sharing.
That was amazing. Really, really well delivered with the time crunch. Thank you so much, everybody, for attending. If you have any questions, please feel free to ask the chat. We'll read them out and answer them. We'll be here for a couple more minutes. Thank you, Philip. Thank you, Harold. Thank you, Lordrick. Thank you, Maddie, Raja, and a huge shout out to Jamika. Thank you, everybody who attended. I hope you enjoyed this. We went through a long journey of 6 notebooks. We learned the very basics of Python. We learned a bit of astronomy. We looked at some real data collected by real scientists. We generated our own catalogs, and we learned how to simplify very, very complex code using the power of Python, and how to recreate real, actual research results. So hope you all developed an appreciation for Python. Hope you all will keep on learning about this language. Remember, if you have any questions, you can ask them in the Slack channel. And even when we're not around and you are coding, Google is your best friend. Stack Overflow is your best friend. If you can't find the solution to your problem there, you're probably not searching with the right keywords. And if you really, really can't find it, then congratulations, you have reached a really new level of programming that not everybody does. Anyway, Anand, do you have anything to shout out about Quest programs? I can pass it on to you. Feel free to unmute and say something about SIP or the other Quest programs if you want. Please, and everybody, if you like this, please tell your friends, your classmates, and anybody else who might be interested in taking this to sign up for PyaR. We will be offering one more session sometime later this year, probably sometime around November. We offer 3 to 4 sessions, 3 to 4 offerings a year, and they're all free. They're always free. All the recordings are uploaded. The recording of this session will be uploaded to YouTube. The first 2 sessions were recorded, and the recordings were sent out to you. So please check your email inboxes. And yeah, please tell everybody to sign up for PyaR. If you are here for SIP, well then, good luck with your program. Check out SIP, sip.ucsa.edu. Check out Shadow the Scientist, another great free program from Quest, from the Quest umbrella. Under the Quest umbrella, where you can actually watch Raja, his team, and many other scientists of other groups collect data live in in observatories or live for other kinds of sciences in labs or in the field. You can sign up for free. Go to shadow.ucsc.edu. Somebody has asked, can we still sign up for SIP 2024? No, unfortunately you can't. But if you're a high school student, maybe you can next year, if you'll still be a high school student then. Check out sip.ucsc.edu. And if you know any high schoolers or anybody who will be a high school student next summer, please tell them about it. SIP is a great program that runs throughout the summer. It provides real research mentoring by putting high schoolers in actual research groups and letting them participate in real actual research, as in the projects are not made up for the sake of the program. There are real actual research programs and the interns participate in real research work. And there are need-based scholarships, so please put in an application if you meet the requirements and you are interested next. Yeah, with that, I think we should call it a day. If you have any questions, please put them in the Slack channel. Thank you everybody for attending, and goodbye. Lordrick, I think you are the host. If you can end the meeting, please go ahead.